Hello everyone, welcome back. So, in the last class we looked at the symmetry boundary condition and the periodic boundary condition. Okay. So, there is it is very important, students are often confused between this symmetry and the periodic boundary condition. So, the symmetry is basically there is no flow across the symmetry plane. Okay. So, it is basically a mirror. Okay. On the other hand, periodic is basically a repetition of the same thing. Okay. They are cyclic. Okay. So, that is one of the things which is very important, and periodic further we saw that it can be translational periodic or the rotational periodic. Okay. If it is around let us say around a shaft or something, okay, where it is rotating at certain angle, then it is a rotational periodic, and let us say it is on a plane, okay, and it is repeating at certain distance, okay, then it is a translational periodic. Right. Now, next is the axisymmetric boundary condition. Okay, this is also there are multiple versions of this. I think in open form it is called as the wedge boundary condition. Okay, it is influent. There are different ways of implementing it. You can have a 2D geometry, and you can have you can basically try to simulate a 3D geometry in a 2D plane if the flow is axisymmetric. So, that is all axisymmetric 2D, and then you can also have the sector. Basically, you can have a finite angle, and you can also try to simulate using a 3D code. Right. So, what is axisymmetric? So, let us say you have a nozzle. Okay, this is one of the shape of the nozzle that I am talking about. So, you can see here, let us say this was my nozzle. Okay, this would have been my nozzle, and now you imagine this in 3D. Okay. So, basically it is rotated like this. Okay. So, around this it is basically 360 degree nozzle. Okay. But you would expect that let us say flow is coming at a 0 degree angle. Okay. So, the same basically you take any plane in the azimuthal direction, you will have the same flow, right. So, in the mean sense, right. So, then what you can do, you can basically use the axisymmetric boundary condition. So, what is axisymmetric boundary condition? So, basically at the axis, okay, there is symmetricity. Okay. So, you go to any azimuthal plane, okay, any theta, okay, 10 degree, 20 degree, 30 degree, you will have basically the same result. Okay. So, then you can reduce it, either you can let us say if you have a 3D plane, now I am taking this view. Okay. So, this view, either you can take just this plane, okay, this is my axis, let us say my 0 0, this is 0 0 prime. Okay. So, this is my 0 0 prime. Okay. And then you can either take only this plane, this is my 2D plane now. Okay. So, that is axisymmetric 2D, or you can take a very thin slice here. Okay, just maybe just one section or one grid point here, that is called the wedge boundary condition, or maybe you can take a plane like this, okay, at a certain angle. So, this is basically the sector. Okay. Typically all of this, I mean if the flow is completely axisymmetric, okay, it should all work on the same concept, my del by del theta is equal to 0. Okay, there is no variation in the theta direction. If you have a 3D code, then you would go for let us say wedge and sector. Okay. If you have a 2D code, then you can basically use or apply some source terms at this boundary, which is the axisymmetric boundary on the axis, so that it can basically give the effect of the 3 dimensionality, right. So, there are again this is used for reducing the complexity and computational cost of simulation involving cylinder or rotational symmetry, right. So, in the first case, which is the 2D axisymmetric, the domain is reduced to 2D, just like it is shown here. Here I, instead of basically simulating this entire thing, what I am doing is basically I am only simulating one 2D plane. Okay. So, my grid is in fact none of this will be there, and you can just simulate one 2D axisymmetric plane. Okay. You can make a grid like this. Okay. So, you can make a grid like this, okay, everywhere. Okay. So, of course, it will not cross, and you can do the simulation. Okay. You can have maybe if there is a there will be some inlet here, outlet here, on top you can have the wall, okay, if it is a nozzle, okay, and then at the bottom you can have the axisymmetric boundary condition. So, there is no variation with respect to theta, okay, and phi is equal to there is no variation in theta here. So, basically R g, and if it is time dependent, then phi R g t. right. So, again we are talking about the coordinate system with the cylindrical coordinate system r z theta, right. What we do in many codes it has been implemented is basically you use some source term at the axis, okay, to enforce the axis symmetry. Okay, I will not go into the detail here, I will just show you what is happening, and you can if you are writing a code you can figure out how to ensure that basically there is a symmetry, and symmetry concept we have understood that there is no normal flow that is happening there. Okay, in the axis symmetry it is further that your del by del theta is 0 even in the case of wedge or sector. Now, it is not 2D geometry, it is a 3D geometry, and in the case of wedge as I told you that typically you have just one cell, okay, and in the sector you can have the finite portion, maybe 10 cells or 20 cells or something like that. Okay. So, in the case of wedge, for example, this example I have taken from the open form. Okay. So, you can have one patch here and one patch there, okay, and you apply the wedge boundary condition there. So, just like the symmetry that we had here, there will be no normal flux, and all others are basically calculated using the Neumann condition, right. If you have a completely 3D code, okay, and you want to do 3D simulation, you can probably right now it is less than 5 degree, you can maybe take 20 degree or 30 degree, that will become the sector boundary condition. Okay. So, it need not be just one cell, but there can be multiple number of cells in the azimuthal direction. Okay. So, the one thing that I talked in the last class, that unlike the rotational periodic which was discrete symmetry, that means you have delta theta which was fixed, and the flow was repeating at that delta theta again and again, just like you have in let us say on turbine shaft. Okay. But in the case of axis symmetry, it is continuous symmetry, delta theta can be any value. Okay. So, it is true for all alpha. Okay. So, you take 5 degree, 10 degree, 20 degree, 30 degree, 50 degree. Okay. As long as you enforce the axis symmetric boundary condition correctly, you are assuming that there is no variation in the theta direction, and they all should give you the same result, right. So, if you are the flow is straight and you want the fastest result, the 2D axis symmetric is probably the best choice, but you need of course the 2D code. If you are using a 3D solver, okay, like simple pipe and nozzle, then the wedge boundary condition just one cell across the azimuthal direction is okay. If the flow is rotating or have complex 3D features, okay, then maybe like a swirl injector or all, then you can use a complete 3D code, and you can use the sector boundary condition. Okay. So, this is about the axis symmetric boundary condition, okay, and they all basically usually talked like periodic, symmetric or axis symmetric. Okay. They are very easy to understand and very easy to implement boundary conditions in your code, because you do not have to do anything. Whatever information is coming from one cell, you pass it to another cell. Okay. There is no special treatment, there is no Dirichlet value, except that you say that okay, in the case of symmetry the velocity normal goes to 0. Now comes the most important thing, which is the how do you trade the inlet and outlet boundary. Let us say I talked about this example of flow past turbine blades. Okay, this is your domain. Okay, this is how you make, and the top and bottom you say okay, my periodic, these are all periodic. So, this is periodic. Okay, this is all periodic. Okay, because the blades are repeating, but this is my inlet and this is my outlet. So, how do you treat them? Okay. Also, like let us say there is a aerofoil or there is a flow past a cylinder. Okay. Then you have far field boundary condition. Okay. If there is an aerofoil kept here. Okay. So, depending on how you make a grid, okay, you can have far field or inlet and outlet. Okay. So, we will look at these boundary conditions in the next few slides. Okay. So, first thing is the velocity inlet. I think I briefly mentioned it in the first class on the boundary condition. So, we basically specify the velocity, okay, and we extrapolate the pressure from the interior. Now, this question comes many times that why can't we specify both the pressure and the velocity, right. Typically either you put pressure and the velocity is extrapolated from the interior, or you basically velocity and put the pressure is extrapolated from interior. So, you can't have both the specification of the pressure and the velocity. Okay. There are multiple reasons for that. One is that, for example, let us say if you put a pressure, or put a pressure as boundary condition. Specify means it is fixed, you cannot change it, the code also cannot change it, that is fixed on the boundary. Okay. And let us say your velocity is also fixed, okay. They are both calculated from your code, you specified both of these things. Now, this because a numerical thing it will run and it will give you the value which is P naught, which is an indication of the energy, stagnation or total pressure. Now, if both are fixed, this value of P naught will change. Okay, that means your total stagnation pressure is changing, okay, which is physically incorrect. So, let us say you have something coming from a reservoir, okay. So, you have this stagnation pressure and then you have some test object here and then you have some measurements here. Okay. So, your stagnation pressure P naught is fixed, unless you supply some additional energy, your P naught should not change. Now, once you specify the P and V, there may be slight change because these both things have been fixed. So, it will not basically what will happen that it can change your total P naught. So, what we do is that we fix the P naught, okay, and then fix either P or V, okay. So, that basically your P is fixed and the V will be adjusted such that it goes to P naught, that the value you desire, okay. Or if you fix V and P will be adjusted from the code in such a way that P naught is fixed, okay. So, fixing P naught and P, fixing P naught and V is fine, but fixing P and V is basically it is saying that there is no scope for the code to basically float these values, I mean to change these values, and that can lead to basically the code can basically diverge. Okay. This is one region, there are multiple regions. One is thing is that we will talk about something called Riemann invariant. Okay. So, that is a combination of P and V. Okay, those are Riemann invariants. P basically V and A, the speed of sound and the velocity. Okay, but speed of sound depends in turn depends on the pressure. Okay. Now, Riemann invariant what it says, if you look at the compressible literature, which we will discuss shortly, that you have something which is coming in, some characteristic coming in and some characteristic coming out. Okay. Something is coming from inside to out, something is coming from outside to in, right. So, let us say you fix the P and V both, right. So, now when you are trying to calculate these Riemann invariants or whatever value that is coming out, okay, there will be a mismatch, because one thing can get in, let us say velocity is getting in and pressure is coming out, okay. One is incoming and another is outgoing. So, in the combination of both, which is called which can be Riemann invariant, I mean it can satisfy whatever is coming in and whatever is going out. If you specify both of these, one of them will not obey. So, either the characteristic will completely go in or it will completely go out. So, you can't have the combination of things, something going in, something going out, right. So, in the case of supersonic flow, you can try doing this, because supersonic flow, as we will shortly see, either all the characteristics all incoming or all outgoing, right. So, in that case you can basically specify both P and V and you can work it out. Okay. So, so another thing is that as I mentioned earlier is that it is usually used for the incompressible flow, this velocity inlet is boundary condition. In the case of supersonic flow, even in high subsonic compressible flows, so there is no information that can travel upstream. Okay. So, this boundary condition is poorly posed. One is that because supersonic all the characteristics are basically moving in. Okay. So, there is no information that travels upstream. So, this boundary condition cannot be applied. Another thing is that you have, let us say you fix the velocity v. Okay. Now, because of these waves, even in the compressible flow you have basically some fluctuations coming due to the waves. So, your v is not fixed, the v prime is always coming. So, it is very difficult to fix the velocity in the compressible flow. Okay. There will be always be some perturbation or some fluctuation in the velocity. So, that is why it is not a good boundary condition, the velocity inlet is not a good boundary condition for the compressible flows. Okay. But in the incompressible flow, let us say you know the speed of a car or speed of an aircraft, you can just give that speed, you can make the car constant stationary or the aircraft stationary and give the speed, the opposite speed to the air, okay, and that will give you the same result. Okay. But if the flow is compressible, then you have to basically make sure that you respect the physics, and the physics says that there are some characteristics which are traveling, there are characteristics incoming. That means you can think of some, there are waves incoming and there are some waves outgoing, okay, and they will change the velocity. So, it is a better idea to think in terms of energy in the case of compressible flow, and a good way of thinking about energy is the P naught, okay, basically the total stagnation pressure. Okay. So, that is the reason it is not used in the compressible flows. Okay. Yeah, and if you are using, let us say, P and V both. Okay. So, I mean in the compressible flow, okay, if you try to use this velocity inlet in the compressible flows, okay, so what will solver do? It will try to adjust extrapolated pressure to match the fixed velocity. Okay. So, then it can result into some shock waves, spurious shock waves at the inlet. Okay. So, that is why this velocity inlet is not used. If you try using it in a compressible flow, you will see that either your solution will diverge or it will give you spurious waves. Okay. So, yeah, so it is good for thermodynamic flow, but in the incompressible or very low compressible regime, okay, where velocity is known. Okay. The another simple boundary condition which is often called outflow or the zero gradient boundary condition, and I think in the case of open form they call it zero gradient boundary condition, some solvers call it outflow. It is basically what it is saying is that your flow is fully developed. So, you make the domain sufficiently far, that flow is fully developed. So, there is no gradient there. Okay. So, whether you take this point and this point, they are both the same. So, there is no gradient in that direction. Okay. So, they are called the zero gradient boundary condition. So, it requires fully developed state. Okay. That means, your boundary should be sufficiently far, okay, and the gradients of variables in the normal direction are 0. So, that is what is required, and this very simple boundary condition, all you need to do is that when the ghost shell you require, you put the point which is the first interior point. So, in this case let us say these are my ghost shells, okay, and these are the values which are basically my interior n shell here, okay, this is the my n. So, you just copy the value, so rho n you put the rho g equal to rho 1. So, there is no gradient here either in velocity or in pressure or density in any flow. Okay. So, this is only applicable when it is fully developed. It helps in avoiding artificial disturbance, allowing the flow to exit smoothly, okay, but the criteria should be sufficiently large and it should be the fully developed flow. Okay. Both are basically related. Okay. So, we looked at some very simple boundary conditions, one is the velocity inlet and other is the outflow zero gradient, which is true when the domain is sufficiently far away. Okay. Now, let us get into the compressible flow. Okay. So, the one thing is that we are going to repeat what we discussed in the 5th week, okay, and if you recall we discussed different forms of the Euler equations, and one of the forms that we discussed was the characteristic form, right. So, we looked at we took the Euler equation in the primitive variable form, and then you looked at the eigenvalues and eigenvectors, okay, and then we analyzed those eigenvalues and eigenvectors. Okay, we found that when it is an hyperbolic system and all the eigenvalues are real, okay, so and all the eigenvectors are different. So, let's quickly go through that derivation. Okay. So, what we did is basically we will do it for 1D. Okay. Now, you may ask the question that most of the flows are 2D or 3D. So, why you are doing it 1D, right. So, even if the flow is 2D or 3D, what we are interested is basically what is the flow which is coming normal. So, let us say it is 2D one. So, you have this normal direction, okay, and there may be a flow which is happening here or here, whatever direction you have. So, what you have to do is take is basically take u dot n, okay, which you call it as a u normal or u perpendicular. Okay. So, you basically think then it is a locally 1D flow, which is you can show this as this is the flow and there is a normal here and this u dot n is basically passing through it. So, this is locally 1D flow, right. So, write this 1D flow here, 1D flow equations here. I will also basically show it what happens to the other velocity components. Let us say you have v and w also, the tangential component you can call it ut1 and ut2. if it is 3 dimensional, right. So, what happens to those components also, right. So, this I am repeating what we discussed earlier. So, this is written in the primitive form or the quasi linear form, and we have 3 components rho, u and p. This is mass equation, this is x momentum, and these are Euler equations with no viscosity here, okay. And this is energy. Yeah, another question you may ask is why we are basically discussing the Euler equation, right, because the most of the flows are viscous. The argument for that is that you can analyze this thing, you can get the characteristic for the Navier-Stokes also, but they are fairly complicated because of the second gradient term coming due to the viscosity, and much more complicated in the compressor flow. But let us say you try to do any simulation, let us say around this aerofoil or something, you will have basically the far field boundary, okay, or even the maybe the inlet and outer plate sufficiently far away from the body, so that the viscous effects are negligible. You can neglect the viscous effects here. So, it makes the things more easy to handle, and it is it is a good assumption that sufficiently far from the boundary, okay, the viscous effects are not that high. The viscous effects will be high in this region, right, in the boundary layer mostly. Right. So, these are my this is the equation that I have written in this matrix form, okay, and the idea is to get eigenvalues and eigenvector of this matrix AP, which is the matrix based on primitive variable. So, how do you do that? Basically, you take delta AP minus lambda I, this is a determinant of AP minus lambda I. So, you will have basically u minus lambda here, u minus lambda here, u minus lambda here, and take a determinant of this. Okay. If you do that, okay, so this will be u minus lambda and u minus lambda a square, right. So, gamma p by rho, this will become a square. This is u minus lambda and this is u minus lambda square minus gamma p by rho, which is a square. So, then we will have basically 3 components, okay, u minus a, u and u plus a. Okay, now I have to get the eigenvector. So, first I will get the right eigenvector. So, this is basically now we are using the right eigenvector here. Okay, so, my AP is there, my lambda is there. You know how to get this right eigenvector. Basically, you do this AP minus lambda I and you say when it goes to 0, okay, when the determinant goes to 0. Basically, looking for a null vector for which this matrix AP minus lambda I is going to, the determinant of this is going to 0. So, let us say you take this lambda to equal to u here, right. So, what will happen, this AP minus lambda, that will become 0, rho 0. So, I am doing minus lambda minus lambda minus lambda here, in this case lambda 2, lambda 2, lambda 2, this will become 0, 0, 1 by rho and 0, gamma p and 0, right. So, what will be the null vector which will give you the 0 vector here, that will be 1 0 0, right. If you multiply this with 1 0 0, take this matrix, okay, multiply with this 1 0 0, you will get this null space, right. So, this is the right eigenvector corresponding to this. Okay. Similarly, you can take u minus a, you will get this eigenvector. Similarly, you can take u plus a. So, basically instead of lambda 2, you use lambda 1, and then the idea is to look for the null space when for this particular matrix. Okay. So, yeah, this is little bit of linear algebra. If you know how to get the eigenvectors, you can work this out. Okay. So, these are the basically left right eigenvector. You can get the left eigenvector also, which is basically the inverse of this right eigenvector. So, this is, you can have an R matrix which is basically R 1, R 2 and R 3, okay. And then you multiply. So, this is your original equation that we had, and how did you get to the characteristic form earlier? So, you multiply with the left eigenvector here, okay. So, L dV by dt and L AP dV by dx, but L AP just like we had basically AP R equal to lambda R, okay. So, now in the case of left eigenvector, L AP equal to lambda L. So, this L AP can be written as lambda L. Now, we introduce another vector W, which is basically the left eigenvector multiplied by V. Why we are doing this? Because see, lambda is a matrix which is given like this. So, basically it becomes linearly independent. Okay. Now, we have got 3 eigenvalues, okay, u minus a, u and u plus a. So, we are trying to get something called characteristic compatibility equation, which is basically instead of having this coupled equation, sorry, this coupled equation, okay, we will want to get an equation which is decoupled. This is a decoupled equation. If you can get W, which is nothing but L into V, L you can easily get by doing R inverse, okay, and V is the primitive variable, you multiply this, you will get the W. Now, there will be 3 equations for this also, but they will be decoupled because lambda is decoupled, okay. This is U minus A, U and U plus A, okay, and all the other elements are 0, correct. So, this also shows that all the equations are hyperbolic, okay. Of course, U minus A, U and U plus A all are positive, okay. This is how you get this L equal to R inverse, okay. This is R, and this is how your del W by dt plus lambda del x will look like, okay. And you can write in a decoupled form. So, I got this W1, W2, W3 by doing LV, okay. So, this you can go back and work it out. So, now I am writing this in decoupled form. So, each equation is, it is like a linear convection equation for W1 and W2 and W3, and what is the convection speed is basically lambda 1 and lambda 2 and lambda 3, okay. And for the lambda 1 you have U minus A, lambda 2 is the pure entropy waves, okay, and lambda 3 is basically U plus A. So, you can see that lambda 2 there is no change in the velocity. So, this is lambda 2 and you have this wave strength W 2 is rho minus P by A square, there is no velocity here, okay. So, there is no change in velocity across the contact discontinuity, okay. So, that is what I studied earlier, and this is W1 and W2, it has got these are basically acoustic wave, it has got both U and P, right. So, yeah. So, now we have got 3 characteristics. So, C minus, which is lambda minus A, okay, and the equation is del W1 and which is given by, so W1 is given here, P by 2 A square minus rho A by 2 A, the same thing is here written here, okay. So, these are called the characteristic compatibility equation. So, this is the del W1 is equal to this equal to 0 along the characteristic. So, these are basically you might just like you have this expression du by dt plus C du by dx equal to 0, right. How did you solve this problem? So, you have u x t is equal to at any given time is equal to u 0 x minus a t, right, x minus c t in this case, c is my convection speed. So, similar thing is here also. Now, we have 3 different equations, okay. So, one is del w 1 by del t plus lambda 1 del w 1 by del x, okay. So, this is one of the convection equation. So, so w 1 is being propagated at a speed of lambda 1, okay. So, now you can show that I mean basically the delta w 1 will be 0, okay, and then you can write you can simplify it, just multiply with 2 a square, that will give you this, and this is along the dx by dt equal to u minus a. Similarly, you can take this entropy equation, and this is nothing but the speed of sound equation that we had. So, if you recall, a square equal to dp by d rho, right. So, this is what is saying. So, this is pure entropy equation. So, you can take this del w 2 del rho minus del a is 1 by a square dp from here, okay, and that will give you the entropy equation, okay, basically the differential form of the isentropic relation p by root of the gamma equal to constant. And finally, for the right running characteristic acoustic, which is the same thing that we have, now you replace minus with the plus, and you will have the third one, which is called dp plus rho a du equal to 0 along dx by dt equal to u plus a. Okay. So, now the crux of today's lecture is that we have got 3 waves, okay, u minus a, u and u plus a, okay, and for each wave we have a characteristic compatibility equation, okay. One is dp minus rho a du equal to 0, another is the entropy equation, basically this can also be written ds equal to 0, the entropy cannot change, and isentropic relation, and the third one is basically the right running acoustic. In the next class, we are going to look at the consequences of these equations and how they can be used for the inlet and outlet bonding conditions in the compressible flow. Okay. With that, we will stop here. Thank you very much.